Okay, welcome to this video lecture series on the topic of atomic and molecular structure. So, today in this video, I am going to explain about molecular orbital diagram. In the last video, I have discussed about the introduction to molecular orbital theory and its various theoretical aspects. In this video, I am going to discuss about MO diagram, molecular orbital diagram of various molecules. So, we will basically discuss MO diagram of few homonuclear molecule. Homonuclear means both the atoms are same, and we will also discuss few of the heteronuclear diatomic molecules where two atoms are different. They are homonuclear because, as you can see, lithium 2, beryllium 2, boron B2, C2 and N2, both the cases O2 and F2, two atoms are same, that's why they are homonuclear. Whereas carbon monoxide, NO, HF, in this case two atoms are different, so they are heteronuclear diatomic. And also, if possible, we will try to discuss about the applications of MO theory. Okay. So now let us start. So we will first try to discuss about homonuclear diatomic molecule, and then we will discuss about heteronuclear diatomic molecule. So now, as you know that in molecular orbital, generally two atomic orbital they combine and they form the molecular orbital. The number of atomic orbital is equal to number of molecular orbital. So first let us start with lithium 2. So in case of lithium 2, the electronic configuration is 1s2, 2s1. So as you can see, the 2s1, this atomic orbital is going to participate in bonding, that means this one. So 2s atomic orbital of this lithium and 2s atomic orbital of this lithium, they will combine and they will try to form two molecular orbital. Out of two molecular orbital, one will be bonding molecular orbital, another will be anti-bonding molecular orbital, and the electrons will be filled as per Hund's rule by following Pauli's exclusion principle, everything, above principle. So there are two electrons, one from this 2s and another from this 2s atomic orbital of the lithium atom. So these two electrons will definitely occupy the bonding molecular orbital and anti-bonding orbital will be empty. So this is the molecular orbital diagram of lithium 2 molecule. And we have also discussed about the bond order, which is number of electron present in bonding electron minus number of electron present in anti-bonding electrons. So bonding electrons Be I am writing minus non-bonding electron, if we write Nbe, or anti-bonding electron, anti-bonding electron. So number of electrons present in bonding orbital minus number of electrons present in anti-bonding orbital divided by 2. So in this case 2 minus 0 by 2. So here will be your number will be 2 minus 0 by 2, that means the bond order will be 1. So this is the molecular orbital diagram and corresponding bond order of lithium 2 molecule. And this is the energy, that is very important. You must, while you are writing the bond order, you must give the energy sign, or this in this arrow should be like this, so that it seems this is lowest energy, this is highest energy, which I have already discussed. So now if you look at the other molecules, let us consider boron, carbon, nitrogen, oxygen, fluorine and neon. So actually they are quite similar, and so this will be your beryllium, similar to lithium. If we consider beryllium, and if we try to construct the beryllium molecular orbital diagram, you can see that in beryllium also the electronic configuration is 1s2, 2s2. So two 2s molecule two 2s orbital if they combine and they form two molecular orbital, one bonding, another anti-bonding, and these two electrons present in this 2s atomic orbital and two electrons from this atomic orbital, they will try to occupy both the bonding as well as anti-bonding orbital, because one molecular orbital can take only two electrons. So 4 electrons will be distributed as 2 will go to bonding molecular orbital, another 2 will go to anti-bonding molecular orbital, and if we try to find out bond order, then you will find that bonding electrons minus anti-bonding electrons divided by 2, it will give you the value of 0. If the bond order is 0, that means there will not be any bond formation. So beryllium 2 is not stable and beryllium 2 is not found. Some of the ionic state of beryllium 2 can be found, but beryllium 2 is not stable. So it can be very easily explained by drawing the molecular orbital diagram. So now if we go for the other molecule, now this is very interesting, because if we remember only the left side MO diagram, that means this one, then this can be used to for the molecular orbital diagram of boron, carbon and nitrogen, and this side MO diagram can be used to describe oxygen, fluorine and neon. Now what is the difference? If you look out both the diagram, it seems similar, but there is a very important difference between these two structures, and the difference is that the energy of this sigma molecular orbital and pi molecular orbital. If you look at both the structure, then you will see that in case of boron, carbon and nitrogen, pi molecular orbital actually have lower energy than sigma molecular orbital, but in case of oxygen, fluorine and neon, sigma molecular orbital has lower in energy. Now why this happens? This happens because the 2s and 2p interaction, 2s and pi 2p interaction. In case of boron, carbon and nitrogen, this 2s and this in pi 2p, this interaction is very strong. That's why the energy of this pi molecular orbital is lower than the sigma molecular orbital. Whereas in case of oxygen, fluorine and neon, this sigma 2s, that means this sigma star 2s and this pi 2p molecular orbital, this interaction is very low. That's why it is not appearing below of sigma 2p orbital. So it is almost similar to other molecular orbital, but for boron, carbon and nitrogen, this difference is observed, and the reason is you need to remember the sp interaction, that means sigma star 2s and pi 2p, this interaction. Because of this sp interaction, the energy of pi molecular orbital, pi 2p molecular orbital is lower than sigma 2p. So that's you need to remember. Other thing is similar, you just need to enter the number of electrons into this molecular orbital and you can construct the MO diagram for boron, carbon and nitrogen using this MO diagram, and by using this MO diagram you can construct the MO diagram for oxygen, fluorine and neon. You need to just fill up the electrons. We will show in the within next few minutes. So now as I told that the reason behind this is the interaction between 2s and 2p. In case of boron, carbon and nitrogen, the 2s 2p interaction is very strong, whereas for oxygen, fluorine and neon, this 2s and 2p interaction, this interaction is not that much strong, whereas in this case this and this interaction is very strong. Because of that, this is lower in energy, whereas this is not lower in energy. So this is the reason you need to remember 2s 2p interaction. This is very important, 2s 2p interaction, because this is the actual reason why it appears. So now if we try to fill up the MO diagram with electron, then how it appears? In case of boron, carbon and nitrogen, the MO diagram is as I this one. So all the three cases MO diagram will be same, only thing is that number of electrons will be different. In case of boron, B2, what happens? Because in this case 2p, how many electrons are there in case of 2p? Only one. So from both the boron, one electron will come, and 2s, sigma 2s and sigma star 2s, they will remain as it is, because all the cases it is 2s2, right? For boron it will be 2p1, you already know it. 2s2 2p1. For carbon it will be 2p2, 2s2 will remain as it is. and for nitrogen it will be 2p3, right. So only the number of electrons in p orbitals are increasing, 2s will remain same. So sigma star 2s and sigma 2s, they will have the similar electronic configuration, only change will be in the case of your this side. So for B2, both the pi molecular orbital will occupy single electron. In case of carbon, they will occupy double electrons. In case of nitrogen, they will occupy pi molecular orbital as well as sigma 2s. So this is pi 2p, this is sigma 2p, right? Yeah, this is your sigma 2p and this is your pi 2p, as you can see. So both pi 2p and sigma 2p will be occupied. Now this will be your boron, carbon and nitrogen. In case of oxygen, fluorine and neon, again the sigma 2s will be remain same, because in case of oxygen your electronic configuration will be 2p4, right. Then for fluorine it will be 2p5 and for neon it will be 2p6. So for oxygen this will be your electronic configuration. Now you can see that now the antibonding pi star at molecular orbital has a single electron. In case of fluorine it is double electrons. In case of neon all the orbitals are completely filled, right. That means Ni2, this is nickel 2 is not possible, because the bond order will be 0. That's why they are not found in the diatomic state. Because of this, stability is very less. Now let us discuss about the bond order and other thing. If we look at the bond order, so this is your lithium, beryllium, boron. It is very easy. Already I calculated for lithium it is 1, for beryllium it is 0. These two already we have calculated in the previous few minutes. Now for boron, if we calculate, as I told, the number of this one will be, you can actually don't have to consider, because this will always remain filled. So for boron there are 2 electrons in bonding and there is no electron in antibonding, so 2 minus 0 by 2, so bond order is 1. In case of carbon there are 4 bonding electrons and no antibonding electrons, so 4 by 2, that is 4 minus 0 by 2, so bond order is 2. In case of nitrogen there are 6 electrons in bonding molecular orbital, there is no electron in antibonding molecular orbital, so 6 minus 0 by 2, so 3. That's why in most of the cases NN triple bond is found, and this is very much strong and lots of energy is required, so N2 is very stable. That is the reason in many of the organic reactions nitrogen atmosphere is used as an inert atmosphere. So this is very important to remember. Because of this high bond order, the bond strength is very high. It's very difficult to break this bond, and that's why nitrogen is very stable. Now if we discuss about bond order and magnetism. Now why a molecule become paramagnetic? If it contains unpaired electrons, then it becomes paramagnetic. If it contains paired electrons, then it's diamagnetic. Just remember this simple formula for time being. So for lithium it is definitely diamagnetic. For beryllium there is no point because it's not stable. For boron it is paramagnetic because single electron is there, so they are unpaired electron, right. And for carbon it is diamagnetic because both the electrons are filled, so they are paired electrons. In case of nitrogen also it is paired electrons. So nitrogen is diamagnetic, carbon is diamagnetic, whereas boron is paramagnetic. That's why sometimes boron is used for in many imaging applications, where magnetic imaging applications. Now if we look at for other molecules like your oxygen, so again you can put the electrons and you can draw this diagram very easily now. So in case of oxygen, the number of electrons present in bonding electrons, you can see that it is 4, antibonding 2. So if you calculate bond order for oxygen, it will be 2, 4 minus 2, so this, sorry, 6, because this is your 2, 2, 4 to 6, this is bonding electrons and 2 is antibonding. 6 minus 0, sorry, 6 minus 2, 6 minus 2 by 2, so it will give you 2 bond order. And you can see there are 2 unpaired electrons present in case of oxygen, so that's why oxygen is paramagnetic. Very important to know. The reason why oxygen is paramagnetic is that this is the reason, because it has 2 unpaired electrons. In case of fluorine, bond order you can easily calculate. There are 6 bonding electrons, so 6 minus 4 antibonding electrons divided by 2, so it will give you bond order 1. For fluorine the bond order is 1, for oxygen it is 2, and it is diamagnetic because both the electrons are paired, so that is diamagnetic, whereas this is paramagnetic because electrons are unpaired. In the case of neon, the bond order will be definitely 0 because there are 6 bonding and 6 anti-bonding electrons. Bond order is 0, so neon is not found. There is no point of diamagnetism and paramagnetism. So oxygen is paramagnetic, and we can very easily prove it. There are various ways to prove it. So this is very important. The oxygen is paramagnetic, whereas fluorine is diamagnetic. And the reason of the paramagnetism is that if you draw the Lewis structure, then you will not able to explain it. That's the one advantage of MO theory, or it can say that applications of MO theory. The paramagnetic character of oxygen was really actually surprising to the people where this MO diagram, MO theory was not discovered, because that time Lewis theory was very famous, and when people just knew that according to Lewis theory all the electrons are paired in oxygen, so it should be diamagnetic, but in the experimental it was found that it is actually paramagnetic. So they tried to explain it based on MO theory. By the time MO theory was discovered, and they were able to explain that because of the presence of this unpaired electron in pi molecular orbital, anti-bonding molecular orbital, oxygen is paramagnetic. So this is one of the good applications of MO theory. There are various number of applications in there. Now from MO theory, one very important point that you need to remember, you need to understand, that is called HOMO-LUMO and energy gap. What is HOMO, what is LUMO, and what is called energy gap? So we will try to understand three things clearly, that what is HOMO, what is LUMO, and what is called energy gap, because this is very important for various branches of science and technology where energy gap actually plays important role. For example, in electronic industry, electrical industry, it's had a huge role, right? So now HOMO means highest occupied molecular orbital. So if this is a molecular orbital diagram, so this is the this is the MO which we can call highest occupied, because its energy is highest and it is occupied electrons. So highest occupied molecular orbital will be this, and lowest unoccupied molecular orbital is LUMO. So this will be your LUMO, which is lowest in energy and unoccupied. And the energy gap between this highest occupied molecular orbital and lowest unoccupied molecular orbital is known as HOMO-LUMO gap or energy gap. Sometimes in the case of solid state it is also known as band gap. The gap, energy gap between HOMO and LUMO. Right. So let us take an example. Let's say this is an MO diagram which is for carbon monoxide. We'll discuss later on. So this is the LUMO, lowest unoccupied. In this case, this is the LUMO, because this is the unoccupied and it is lowest in energy. That's why lowest unoccupied molecular orbital. And this is the HOMO, because this is occupied and highest in energy. So what will be your HOMO-LUMO gap? This is the HOMO-LUMO energy gap, 5 sigma and 2 pi, because this is the energy gap between highest occupied molecular orbital and lowest unoccupied molecular orbital. This is also called energy gap, right? So now we will discuss about few of the heteronuclear diatomic. As I told that this was all homonuclear. Now heteronuclear. One of the best example of heteronuclear diatomic molecule is carbon monoxide. Now at first you need to understand the electronic configuration for any kind of MO diagram. If you want to construct the MO diagram, the first rule is that you need to completely understand the electronic configuration of that atom, otherwise you will not be able to construct it. So for carbon, the electronic configuration you all know, 1s2 2p2. For oxygen, 1s2 2p4. But here the interesting point is that both the atoms are not same. That electronegativity is not same. Now oxygen has higher electronegativity than carbon. So all the orbital of oxygen will be lower in energy because of higher electronegativity than carbon. So while you are constructing the MO diagram, that point you need to only keep in mind. That's all. Other will be automatically done. It will be similar as for the homonuclear molecule. So I am trying to explain here. So this is side carbon orbital, atomic orbital. These are the oxygen atomic orbital. As you can see, they are little bit lower in energy. If you just look at this is energy, right? then they are lower in energy because of its highest electronegativity. So that is the only difference. So this is very, very important because if we forget to draw like this, then definitely it's meaningless. So now for 2s there is no problem because electrons will be occupy all the bonding and anti-bonding orbital. Forget about this 3 sigma 4 sigma. You can talk about that this is 2s sigma 2s, this is sigma star 2s, right? This is sigma 2p, this is pi 2p, this is pi star 2p, this is sigma star 2p, like that you remember. The similar way you have done it with homonuclear. So now it has 2 electrons in the p orbital in carbon, so there are 2 electrons, this is carbon and this is 4 electrons, total 6 electrons. So these 6 electrons will occupy 3 bonding molecular orbital. So anti-bonding molecular orbitals are completely unoccupied. So what will be the bond order? Bond order will be 6 because number of electrons in bonding orbital is 6. There is no electron is anti-bonding, so 6 minus 0 by 2, bond order is 2. Bond order is 3. That's why most of the time the carbon and carbon monoxide it is very, very stable and it has 3 bonds. Very difficult to break this one. That's why it's stabilized also. So now another heteronuclear diatomic is NO, nitric oxide. You can again the same thing, only thing is that you need to draw the oxygen atomic orbital a little bit lower in energy because oxygen has higher electronegativity than nitrogen. Other thing will be same. In this case nitrogen has 2p3 and oxygen has 2p4, so there are 7 electrons. So there will be 6 electrons in the bonding and 1 electron will be anti-bonding, so bond order will be 2.5. That's why NO is not very much stable rather than NO plus is stable. So it will always release, it will always try to release this electron, and as soon as it releases it becomes the bond order increases to 2.5 to 3 because number of electrons in anti-bonding will be 0. So it will have much more stability than NO. So that's why NO plus has huge number of complexes. In inorganic complexes in coordination chemistry, NO plus has huge amount of complexes. It's a very good ligand, very, very good ligand because of this property, right? So the bond order of NO is 2.5. So this is about the MO diagram of heteronuclear diatomic molecule, which is nitric oxide or NO. Now similar to that, if I consider HF, then again everything will be same. Only thing is that you need to consider that in this case hydrogen has only 1s1, so it will combine with 2p orbitals of fluorine, and fluorine has very high electronegativity, so energy difference will be very, very high, and that's why most of the and then if we form the molecular orbital diagram, there are 4 atomic orbitals, so there will be 4 molecular orbital, 2 bonding, 2 anti-bonding, right? But you can see that only 1 atomic orbital can combine with any of the atomic orbital with 2p. So there will be only 2 1 bonding, 1 anti-bonding, and 2 orbital will remain as non-bonding because they do not have anything to combine, so they will remain as non-bonding. And if you look at all the electrons, they are very, very close. All the molecular orbital, basically all the molecular orbital, they are very, very close to fluorine because of the electronegativity. So most of the electron density will be close to fluorine, and that's why hydrogen got some positive charge and fluorine got negative charge. You probably know it from your plus 2 level that if you write HF, we generally write like this, HF and then delta negative here and delta positive here. The reason is that from this MO diagram, because of the molecular orbital are very, very close to this fluorine, they will reside, most of the electron density will stay on fluorine. And bond order will be definitely 1 because there are 2 bonding electron, because they are non-bonding, so we will not consider this. So 2 bonding, non-anti-bonding, so 2 minus 0 by 2, 1. So that's why it has a single bond. So this is about your molecular orbital theory. Now in the next video I am going to discuss about pi molecular orbital and pi molecular orbital diagram of butadiene and benzene. Okay, so see you soon.